Welcome to G Fun Facts Online. Today, we are going to dismantle the ground beneath your feet. If you were to slice the earth in half like a peach, the school textbooks of the last century would tell you exactly what to expect. You would see a thin, rocky crust, a thick, flowing mantle of silicate rock, a liquid outer core of molten iron and nickel, and a solid inner core of crystallized metal. For decades, we were taught that the deeper you go, the drier it gets. We were told that the volatile compounds, water, gases, and the delicate chemistry of life were merely a surface veneer. We were told the oceans were a lucky coat of blue paint on a dry, dead rock, likely delivered by icy comets long after the planet cooled. That story is no longer true. Over the last decade, and culminating in explosive research published as recently as February 2026, geophysics has undergone a silent revolution. We have found the missing oceans. They are not hidden in lost caverns or hollow earth theories, but locked within the atomic lattices of crystals and dissolved into the hellish metal of the planetary heart. We now know that the Earth is not just blue on the outside, it is soaked to the core. From the hydrated wet zone of the mantle to the newly confirmed hydrogen core, we are standing atop a reservoir that dwarfs the Pacific, the Atlantic, and the Indian Oceans combined. The latest estimates suggest that the Earth's core alone may hold the hydrogen equivalent of 45 global oceans. This is the story of how we found the water inside the stone, the leak that trickles into the center of the world, and the hydrogen battery that has kept our planet alive for 4.5 billion years. To understand the magnitude of this discovery, we have to go back to a mystery that plagued geologists for a century. It is called the density deficit. When seismologists first began mapping the Earth's interior, using the shock waves of earthquakes, they encountered a math problem. They knew the mass of the Earth because they could calculate it from the planet's gravitational pull. They also knew the volume. By analyzing how fast seismic waves traveled through the core, they could determine that the core was made mostly of iron and nickel. But there was a discrepancy. The core was too light. Pure iron-nickel at core pressures, which are around 360 gigapascals, should be denser than what we actually observe in the data. The core was missing about 10% of its expected mass. Something else was down there. There had to be some light element that was diluting the iron, making the alloy frothy and buoyant. For years, scientists proposed candidates like silicon, sulfur, oxygen, and carbon. Hydrogen, the lightest element in the universe, was considered a long shot. Hydrogen is extremely volatile. The prevailing wisdom was that during the violent, molten birth of the planet, any hydrogen would have boiled away into space. For years, the dry Earth hypothesis reigned. It assumed Earth formed hot and dry, and water arrived later via a late heavy bombardment of icy comets. But this theory had holes. The isotopic signature of Earth's water, specifically the ratio of heavy hydrogen or deuterium to normal hydrogen, did not match the comets we measured. It matched the asteroids and the dust of the early solar system. This hinted that water wasn't an alien visitor. It was indigenous, it was baked in. But if it was baked in, where was it hiding? The first crack in the dry Earth dam didn't come from a computer model, but from a piece of trash. In the diamond trade, inclusions are flaws. They are bits of foreign minerals, trapped inside the diamond as it forms, dirtying the gem and lowering its value. For geochemists, however, diamonds are the only time capsules we have from the deep Earth. While the deepest hole humanity has ever drilled is a paltry 12 kilometers, the Kola Super Deep Borehole, diamonds form at depths of 150 kilometers or more. They then ride volcanic kimberlite pipes to the surface at supersonic speeds, preserving the high-pressure minerals inside them before they can degrade. In 2014, a team led by Graham Pearson from the University of Alberta was analyzing a trash diamond from the Huina River gravels in Mato Grosso, Brazil. It was a battered, brown, worthless stone. But inside, they found a microscopic speck of a mineral that had never been seen before in nature. It was called ringwoodite. Ringwoodite is the high-pressure alter ego of olivine, the green mineral that makes up most of the Earth's upper mantle. We had synthesized ringwoodite in labs by crushing olivine between diamond anvils, and we had seen it in shock veins of meteorites that had crashed into other planets. But we had never seen a terrestrial sample. The reason is simple. Ringwoodite only exists between 410 and 660 kilometers deep, in what we call the mantle transition zone. If you bring it up slowly, the pressure drop causes it to revert back to olivine. It crumbles. But encased in the diamond's adamantine pressure vessel, this speck survived the ascent. When Pearson's team fired infrared light at the speck, they saw something impossible. The crystal structure wasn't dry. It was filled with hydroxide ions. The ringwoodite was 1.5% water by weight. 1.5% sounds small, but the transition zone is 250 kilometers thick and wraps around the entire planet. If the Juina diamond was representative of the whole layer, that small percentage translated to a volume of water equal to 3 times the surface oceans. The headlines in 2014 were ecstatic, proclaiming a massive ocean discovered beneath Earth's crust. But we must be clear on the science. This was not an ocean of liquid water with fish and waves. It was water trapped in the rock, like water in a damp sponge or a concrete wall. It was a hydrous mineral reservoir. This discovery solved one problem, where the Earth keeps its water budget. But it opened a much larger door. If water could survive in the mantle, could it go deeper? Could the sponge leak? For a decade after the ringwoodite discovery, the scientific consensus settled on a wet mantle, but a dry core. The core mantle boundary, located 2,900 kilometers down, was viewed as a hard iron wall, rock above, metal below, and never the twain shall meet. The mantle is silicate rock. The core is metallic iron. They don't mix. Or so we thought. In late 2023, a collaboration between Arizona State University and Yonsei University shattered the iron wall concept. They were investigating a mysterious layer that seismologists had detected for decades. Sitting just above the liquid outer core is a thin, patchy skin called the E' layer. In this layer, seismic waves slow down and density drops. The researchers, led by Dan Shim, ran high-pressure experiments to simulate the conditions at the boundary. They took iron, representing the core, and water, which is carried down by subducting tectonic plates, and squeezed them to 135 gigapascals while heating them to thousands of degrees with lasers. What they saw was a chemical massacre. At the boundary where the wet rock meets the molten iron, the water molecule breaks apart. The hydrogen, being small and siderophile, or iron-loving, abandons the oxygen and dives into the iron core. It dissolves into the metal, turning the outer core into a hydrogen-rich alloy. But what happens to the oxygen? The oxygen stays behind and reacts with the silicon in the core. This reaction creates crystals of silica, essentially sand crystals. Because these silica crystals are lighter than the liquid metal, they float upwards, snowing up into the mantle. This was the mechanism of the leak. Here's how the cycle works. First, subduction occurs when tectonic plates drag wet ocean crust down. Second, the slabs sink through the mantle, carrying water past the ringwoodite zone all the way to the bottom. Third, at the core boundary, water chemically attacks the iron. Fourth, the separation occurs. Hydrogen is sucked into the core, and silica crystals are spit back out into the mantle. The E' layer wasn't just a skin. It was a crystal factory and a hydrogen pump. The Earth was stripping the hydrogen from water and hoarding it in its heart, slowly growing a hydrogen-rich layer on the surface of the core. This proved that the core was taking in hydrogen right now, but it didn't explain the massive density deficit of the entire core. The leak was a slow trickle. To explain the missing 10% of the core's mass, we needed something bigger. We needed a deluge. This brings us to the present day, February 2026, and the groundbreaking study published in Nature Communications by Dongyang Huang and Motohiko Murakami. While the 2023 studies focused on the surface of the core, Huang and Murakami went for the center. They sought to answer the question, did Earth form wet from the very beginning? The team utilized a new generation of diamond anvil cells, devices capable of creating pressures not just of the mantle, but of the deep core. They placed iron samples inside these cells, surrounded them with hydrogen, and used lasers to replicate the magma ocean phase of the early Earth. 4.5 billion years ago, Earth was a ball of molten rock. There was no solid crust, no separation of core and mantle. It was a chaotic soup. As the planet cooled, the heavy iron droplets sank to the center to form the core, raining down through the silicate magma. The researchers wanted to know, as these iron raindrops fell through the magma, how much hydrogen did they drag down with them? The results were staggering. The partition coefficient, the preference of hydrogen to bond with iron versus rock, was much higher than previously predicted. Under the extreme pressures of the proto-Earth, iron acted like a hydrogen magnet. The study concludes that as the core formed, it sequestered a colossal amount of hydrogen. The iron didn't just leak hydrogen later, it was born saturated with it. The numbers are difficult to comprehend. The study estimates that the Earth's core contains between 0.36% and 0.7% hydrogen by weight. In terms of planetary mass, that sounds negligible, but the core is huge. When you convert that percentage into water equivalents, since that hydrogen came from primordial water, the total volume is between 30 and 45 times the total volume of Earth's modern oceans. Let's visualize that. The surface water, the familiar blue oceans we know, amount to 1.3 billion cubic kilometers. The mantle water in the ringwoodite layer accounts for roughly 3 to 5 billion cubic kilometers. The core hydrogen represents 50 to 60 billion cubic kilometers of water equivalent. We are not living on a rock with a bit of water. We are living on a drop of rock suspended in a ball of water-infused metal. The dry Earth is a myth. The planet is, by composition, a water world that happens to have a hard shell. Why does this matter? Why should the average person care if there is hydrogen in the center of the Earth? Because the hydrogen core is the engine of our existence. First, consider the magnetic shield. Earth's magnetic field shields us from the solar wind. Without it, our atmosphere would be stripped away, and we would look like Mars. The magnetic field is generated by the geodynamo, the churning of the liquid outer core. For the dynamo to work, the core needs to stay hot and fluid, and it needs convection currents. The presence of light elements like hydrogen is crucial for this. As the inner core freezes, it expels these light elements into the outer core. The lighter fluid rises, the heavier fluid sinks, and this motion generates the magnetic field. The massive reservoir of hydrogen acts as a chemical battery, powering the dynamo for billions of years longer than a pure iron core could. If the core were dry, Earth might have lost its magnetic field and its life billions of years ago. Second, consider the great heat engine. Hydrogen affects the melting temperature of iron. A hydrogen-rich core melts at a lower temperature than a pure iron one. This changes our understanding of the Earth's thermal history. It means the core stays liquid longer, keeping the mantle heated from below. This heat drives plate tectonics, which recycles carbon and stabilizes our climate. The heartbeat of the continents is driven by the hydrogen in the core. Third, this changes the story of the origin of water. The 2026 study effectively kills the comet delivery theory as the primary source of Earth's water. If the core holds 45 oceans worth of hydrogen, and the mantle holds another 3, it is mathematically impossible for comets to have delivered all of that. Earth's water is indigenous. We formed from wet pebbles in the solar nebula. The water was here from day one. The oceans we see today are just the sweat of the planet, the tiny fraction of water that outgassed to the surface, while the vast majority sank to the center. We must now update our mental model of the water cycle. We are all taught the water cycle in elementary school. Evaporation, condensation, precipitation, ocean to cloud to river to ocean. We now must add a new, slower, darker cycle, the deep water cycle. It operates on a timescale of millions of years. First, ingassing occurs as water-laden sediments on the ocean floor are subducted into the mantle. Second, storage happens as the water is trapped in the ringwoodite sponge for millions of years. Third, the Great Leak occurs as some water sinks further, reaching the core mantle boundary, where hydrogen is stripped and stored in the core, while oxygen is ejected as silica. Fourth, upwelling sees the silica crystals and heated mantle plumes rise back up. Finally, outgassing occurs when volcanoes spew steam and gas back into the atmosphere, returning the water or its components to the surface. This cycle suggests that the volume of our oceans is not constant, it is a dynamic equilibrium. In deep geological time, the sea level is determined not just by melting ice caps, but by the hunger of the core. There may have been times in Earth's past when the surface was drier because the interior was drinking the oceans, or times when the interior burped them back out, creating flood worlds. The discovery of the hydrogen core has profound implications for the search for alien life. When we look at exoplanets, planets orbiting other stars, we often categorize them as rocky or gas giants. We look for Goldilocks planets that are at the right distance for liquid water on the surface. But if Earth can hide 45 oceans inside its metal heart, then dry-looking planets might be wet on the inside. A planet that looks like a desert on the surface might have a massive hydrogen reservoir in its core, driving a magnetic field and tectonic activity that could, eventually, support life. It suggests that water worlds are the norm in the universe, not the exception. The water just might be underground. We are entering a new era of geology. The static, layered Earth model is dead. The new model is dynamic, permeable, and wet. The boundary between the core and the mantle is not a wall. It is a membrane. The interaction between the rock and the metal is chemically violent and vital. As you walk outside today and feel the rain, or look at the ocean, remember that you are seeing only the tiniest fraction of Earth's water. The true ocean is beneath you. 400 kilometers down is the ringwoodite ocean, a green crystal sponge holding 3 times the volume of the Atlantic. 2,900 kilometers down is the E-prime factory, ripping water apart to feed the core. And 5,000 kilometers down is the hydrogen core, a metallic sea of iron and hydrogen, holding the ghost of 45 ancient oceans, swirling and churning to generate the magnetic shield that keeps us safe from the stars. The Earth is not a rock with a splash of water. It is a water world, shielded in iron, disguised as stone. Thanks for listening to G Fun Facts Online.